Hey, morning, Sungmin.
Good morning, John. How are
How are
you?
you? I'm doing well. How are you?
Good, how are you?
Yeah, doing great. Been a
Yeah.
few months since we talked. How's
Yeah, long time no talk, yeah.
yeah, how's everything been going with OCP?
Well, there's not much progress in demo design. We're just building the CPU chiplet right now. So
Got it.
I haven't started the project design yet.
I see. Okay.
Yeah.
Well, we can get a update here with everyone.
Mhm.
Hey guys, morning.
I did.
Hi, David.
Let's give let's give everybody a minute or two to join, and we'll get started. I'll, and I will have time in the meantime to sip some coffee, wake up.
Mhm.
Okay, let's get going here. So I was going to the meeting minutes from the last time. Um, we had a discussion about the open source PDKs and open road. I was wondering if you guys have had a chance to take a look into that, have discussions.
Oh, yeah, sure. Can I share my screen?
Yes, please.
Yeah. Um, yeah, so I investigated some available open source PDK and I summarized on these slides. So I took a look into the Skywater and Free PDK, and both are surely open source and available without any permission. We just uh, need to cite uh, the GitHub page. And for CPU design, we also need SRAM cells, right? So uh, for both Skywater and FreePDK, the Open RAM uh, can be utilized to generate the SRAM cells. And yeah, uh, EDA2 is also available. Actually, in our server, we don't have an open road. Uh, we didn't have a open road, so I built that uh, this week, and we're going to use uh, this tool uh, next week.
Okay, cool.
Uh,
Can,
s-
can you make that
yeah.
image for the slightly bigger? For
Oh, yeah,
the,
sure. Hmm.
I think that's the upper row flow. I wanted to see what's available there.
Yeah, so OpenRoad has everything, yeah, from synthesis to routing and
Okay.
sign up as well. Yeah. So I haven't used this OpenRoad, and I'm more familiar with the commercial tools like ICC2 or Innovus. So and we already have free PDK and free PDK standards and SRAM. And we also have a RTL for CPU. So I made the test design with the commercial tool. I've gone through the synthesis, PNR, and sign off, and yeah, with our current resource, yeah, I was able to make the design. So all we have to do
Oh,
is
very nice.
just get familiar with the open road and
Yeah.
run the PNR. Yeah.
Okay. Show me the statistics for this. So
Hmm.
this is 3x3 chiplet. I'm sorry, the CPU is 3x3.
Yeah, 3 millimeter by 3 millimeter, but it's not optimized yet. If you see the cell density is too small.
Yeah.
Yeah, so I will fix the floor plan of macro placement or the cell utilization, and we'll optimize this later. Yeah.
Okay. How small? How much smaller do you think it would get? Like 2x2, it's not likely, right? It will be only 2.5 by 2.5.
Sorry, but a second, please.
Um,
Yeah.
about the size of this block,
Mm.
3x3, with 43%. Does 43% include the SRAMs or without the SRAMs?
Including the SRAMs, yeah.
Okay. So
Yeah, so I have a actually design. So if you see the standards are only, yeah, the utilization is really low in this design. Mm.
okay. This is SRAM small, SRAM small.
Mm.
What kind of frequency did you achieve with this?
I'm sorry.
The
Yeah,
frequency, the maximum frequency for this?
the maximum frequency is 620 megahertz.
That's it's not
Yeah,
bad.
yeah,
If you make it smaller, it should get a little bit faster.
yeah.
Chengbin, the picture
Yeah.
you were showing of the floor plan,
Mm.
is that the cell density? Is it like mostly empty? Is what you were showing there? Yeah.
Oh yeah, so I haven't optimized the floor plan and macro placement for now. So yeah, I will fix this yeah, from this week. Yeah. And the target utilization is about 0.7.
Yeah.
Yeah, so that the empty space empty space to be reduced. Yeah.
Okay. Let's see what did I assume in the original floor plan. Okay, so in the original floor plan, I had assumed 2 by 1.5. So 2 by 2 is probably gonna work just fine.
2 by 2. Okay.
Yeah,
Mm-hmm.
or somewhere in that range. It's gonna look reasonable.
Okay.
With 2 by 2, we should be able to place. If the CPU chiplet is 10 by 10, we should be able to there's 4 CPU instances are gonna fit in in 10 millimeters, right?
Mm-hmm.
So, or we can make the chiplet if we need to 11 by 11 and add, what is it, 4 by 4, 16 CPU cores and call it, hey, this is a 16 CPU chiplet.
Okay, got it. Yeah.
So is your plan to switch this to open road, or is your plan to do it in the commercial tools, just make it smaller?
For me, it's a lot more familiar with the commercial tool. So
Okay.
yeah. So I have one question for this demo design. So are we going to uh open our design file to public, or some providing some scripts as well for the design?
That's a very good question.
Hmm.
I think we want to share with the public as much from this design as possible.
Hmm.
The that said, I have certain things in mind that we probably should talk about how we do that, right? If we did decide to go with fully open road and basically share the flow, how this gets implemented, that's one way to do it. The question is, are we looking for any optimal results? I mean, something that kind of makes sense. And what I have in mind is that the open source synthesis tool does not do forgetting. So power for the core for the each CPU is going for each RISC-V is going to suck, right? But I think it would be good if we can add the design files and the scripts that go with it. So open road would be perfect for that.
Understood.
Kind of
Yeah.
show people, hey, here's a quick way to do a chiplet, right? Everything open source. You can go and replay that and see how it happens.
Makes sense.
Because
Yeah.
I'm assuming with this, we're gonna need to ship some of the additional files and design kits that we're going to generate so that people can use them.
Okay, understood. Yeah. Then I'll go in parallel. I will first optimize the design with the commercial tool, and we'll also take a look at how I can implement with the open road as well.
Actually, can I have a suggestion?
Oh yeah, sure. Yeah.
We don't have to optimize it, right? I mean, it's in practice, in real life, it's good to have some optimized design, right? But since this is just for a demo, we don't have to really go and optimize it much. The level of optimization, what I'm thinking is it should be just something that kind of fits the rest of the flow, right? 3 by 3 right now is probably a little bit on the bigger side. The concern I have is if you go and optimize in the commercial tools and make the flow plan optimal, how well will the open source tools deal with that, right? There's always the concern when switching tool sets, how the tools will behave, right? Whether, right, hypothetically, I'm not saying it will happen, but hypothetically, right, when switching the tool set, you have optimal design in one and then go in the other tool set, and then that tool set cannot close it, right? So what do we do, right? I'm thinking probably take the simple approach, just make this one, this core just a little bit smaller, maybe 2.5 by 2.5, to make it easy for the open source tools to close and just go with that.
Okay.
right? We don't have to have perfect design. We just need to have a working design.
Mm.
If it's 600 megahertz, it's 600 megahertz, right? That's fine.
Mm.
If somebody wants to go and optimize that, they're welcome to do that.
Okay, understood. Yeah, I agree with that. Yeah. Okay.
Right. Yeah, let's not waste your cycles in optimizing something that may end up breaking up the open source tools.
Sure. Okay, understood. Yeah.
What does everybody else think?
No, it's an agreeable thought, David. Yeah.
Yeah.
The only question is once we produce some results based on that, the purpose of the demo probably is not to show the fidelity of the design as much as the fidelity of the flow, right? So we can probably
Yes.
message it out that way.
Yes,
I
exactly.
agree.
This is a workflow demonstration,
Yeah.
not a capability demonstration, right? High fidelity capability demonstration. I agree.
Yeah. Yeah. So, Michael, you brought a separate question offline. So, in fact, Tony and we have all discussed it, the need for staffing up the project, right?
The what? Did that again?
Need for staffing up this demo project. Is that something we all agree on?
David, you'd have to answer that. I don't know who's doing, who's funding this
This is a
project.
question for David. It's a question for David. David and Sungmin, you as well.
Yeah, we definitely, right. We are definitely short on resources, right, and time.
Resource. Yeah. So I had a conversation this week with Professor Andrew Kang from UCSD.
Okay.
And I mean, that conversation was really more in the context of Siemens, synergy with Siemens. But I don't see why we cannot extend it to this also. So he said, not his students, but Punit Gupta from UCLA. I don't know if you know him.
Yes.
Yeah, he works very closely with Andrew Kang. So Andrew suggested that I reach out to Punit Gupta and kind of scope out, what kind of availability he may have. So I can definitely, I do plan to talk to him, both from a perspective of our internal needs within Siemens as well as OCP. I can bring that up with him. So what, especially what kind of expertise we are looking for, David, or interest, let's say? And Sungmin, you are still available through the coming months and quarters, right?
Yeah.
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 So what the expertise we're looking for is there are several things in this project that need to be done. So Sigmund has generated the CPU core, right? We would probably want to get, at least at the CPU core level, we probably want to get a simulation done, a kind of a workload simulation. I think Sigmund had mentioned before that the open Python framework has benchmarks that can be run, right? And that is at the RTL level, right? So get one vector. Basically, what we want to get is one set of vectors, so that then we can take and go and do power modeling and all that stuff, right? Then the next level up is integrating the CPU cores at the chiplet level. What we need is somebody to hook up all the buses together so that CPUs can talk to each other in some way. Then what we need is a actually it's two things. That CPU chiplet was meant to talk to external memory. Tony has provided the HBM, the memory side models. but we don't have chiplet side memory controller.
What is the memory we're going to use?
Tony has provided HBM2 models, which should be perfectly fine. So we are
Okay,
looking
so
for.
are you going to use the HBM2 model that's in the format that was prior to the JEP30, or the JEP30 format that we already provided for the last demo?
So the models I'm talking about are the functional models that can be used to integrate into the chip, not the JEP30 at all. I'm talking basic HBM2 functional models.
Okay, that's like the Verilog model, is it?
Say that again?
Is that the Verilog models?
Large, you said?
Verilog.
Verilog.
Yeah, very long. Yeah.
Okay.
So what we don't have is on the chiplet side, we don't have the memory controller. And right, so that's about the memory subsystem. Then for die to die, we need some interface. There's always the question whether we should use BOW or UCAE, or the models for those are going to be very tough to get, is my expectation. The question is, do we just fake it, meaning if the top module has a bus that is meant to be chiplet to chiplet, we just put IOs in there and we go with that.
So David, those models you're referring to for that communication, is that something that can be covered by the JEP30? Because we already have the UCIe model done, but we don't have the BOW done.
No, I'm talking again about Verilog.
Verilog, okay.
Verilog models, maybe IBS signal integrity kind of stuff.
Okay.
Right. So, Pratyush, that's about what we are missing from this. Right. Once we have the we don't have that. We don't have any of that.
Okay, I'll check with Tony where he got the HBM2E Verilog model from.
It's from Micron.
Oh, it's from Micron. Okay.
Yes.
I see.
But yeah, on the other side, we need some something to drive that HBM.
Right. Okay. Yeah, we'll speak with a couple of organizations, see what we can do here. I see.
Yeah.
Who's the provider of the CPU?
The
Is
CPU
open
core is open source.
Yeah, but I'm assuming it still has a manufacturer for that CPU. Who's the manufacturer for that CPU?
There is no manufacturer. This is all contrived design that we are making just to demonstrate the workflow.
So this CPU is completely designed from scratch. It's not like you're not like taking an Intel CPU or an AMD.
Correct.
Okay. And at what stage do you have a floor? Will you have a floor plan?
Floor plan of what?
Of your design, your demo design.
So first we need to create the CPU chiplet, and then we can start talking about top level floor plan, substrate level floor plan.
Okay.
So Sunwin, the open, the link you shared with us, where you got the RISC-V from, you don't have the collaterals, because the first one, David, you mentioned we need to run functional vector simulations, right?
Yeah.
So it's not in Open Python. It's not available there.
Oh no.
With
It's
Workstream?
available. Yeah, the test bench is available in OpenPython.
Mhm.
They provide the kind of a simulation tool and some scripts for RTL simulation of OpenPython, but I'm not. I have no expertise for RTL simulation, so yeah.
I see.
Yeah. But we can do. Yeah, I checked that last year. Mm.
Yeah, at one point, what we're thinking is due to the lack of those memory controllers and die-to-die interfaces. At one point, what I was thinking is that we basically fake it all, meaning if the CPU, when the CPU is configured for external cache memory, a large one, right, we make it out of SRAMs and just separate it into a separate chiplet and use that bus, whatever bus is going to that memory cache, make it look like a external memory, right? And just use plain IOs and do kind of the same thing for the die-to-die, right? If we generate a subsystem with right, however many CPUs are talking to each other, just take that bus that they're talking to and export it on the boundary and use standard IOs to connect two chiplets together. Right. That's at least that's my thought. One way how we can break up that dependency on different IPs. Which is not technically, it's not totally at least on the memory side, right? I don't think that's totally unfair and unrealistic, because you saw the guys at AMD, they have a separate chiplet which contains all the cache as well. Right? They happen to do it as 3BIC. We're going to do it as 2.5B. That's fine. One consideration for the standard cell library to be used is that Skywater does come with IOs. NAND 45 does not have IOs.
Right. Yeah.
Right.
Yeah.
But again, the question is, can we fake it with a largest buffer in the standard cell library, call it an IO, and drive it that way?
Yeah.
For my research, for our research, we've been using the open source IO, AIB, and we can easily get the RTL, and all the sources are on the GitHub page. And
okay, so
yeah.
you have AIB bus.
Yeah, AIB. Yeah, AIB.
It is the RISC-V 4. Does it support AIB?
Yeah.
Okay, maybe that's one way to do it then.
Yeah.
What do you think, Rajesh?
AIB is a PHY-based interface, right?
It's AIB. I thought it's on chip bus. Is it not?
Yes, it's on chip bus. Yeah.
Yeah.
I
So
see.
we'll just have to take that bus and put it on the die-to-die interface,
Mhm.
and
If
then
you
it can
use,
talk to the other chiplet, to AAB.
I see. Yeah, yeah. That it doesn't have to be BAW or UCIe for sure.
Right? Yeah, if somebody wants to do UCAE or whatever custom interface they want to do,
Mhm.
that's fine, right? As long as we have a bus that kind of sends some signals. we'll be
Just
good to
in
go.
just in terms of industry adoption, I would think that if we wanted to be kind of more agnostic to everything, we'd go UCIe. I've seen much less AIB and BOW in practice. Just food for thought.
Yeah. Yeah. So, John, the predicament that we're in is what industry is adopting in terms of content. It's mostly proprietary, right?
Yeah.
And we are going to have hard time developing open source workflow with a whole bunch of proprietary IPs in there, right?
Yeah, absolutely.
So I think the discussion we had earlier, if the focus is on the workflow, let's say, hey, here's how you do a chiplet, right? It's not commercial chiplet, but here's a workflow, right? If you have something else, you can always go and modify your chiplet. But the important thing is the workflow. I think it's fairly agnostic what the actual content is, right?
Yeah, that's true. I agree with that from a workflow
Yeah.
perspective. Yeah.
Yeah, we can always go and act and act as if that bus is not a simple IO bus, right? We can always go and act as if it's a UCE in simulation, right? We can take the bits, we can take the clocks and simulate it as if it was UCE, right?
Yeah.
No? Yeah, right.
Correct.
Yeah, we
Absolutely.
can even make the bump map if we want to. We can make it look like UCE bump map. The fact that it's not a UCE, but and it's driven by slow IOs is just a something that's not relevant to the workflow.
Mhm.
Yes. So then produce the if there is AAB bus available, then it's a matter of hooking up the that AAB bus on one side to a die-to-die interface, and maybe on the other side to a module that is just memories. I mean,
That is
SRAMs.
sorry. That is just what? I didn't hear the last part. What is it? Oh,
SRAMs.
yeah. Oh, SRAM. Okay. Okay.
Right. Actually, so
Right.
one thing to remember, one thing to know is about the SRAMs. One thing that we did many years ago at SA2 is we generated kind of a benchmark like that, and the I forget which what kind of core we used back then. Maybe it was RISC-V again, but that RISC-V core was depending on like external cache memory, right, which was fairly large. And actually, OpenRAM has two modes. One is in typical case, you would generate the Verilog and like all the Verilog and functional models, and you would generate a GDS2 left def for place and out. For that particular external memory, what we did was we generated only the Verilog files because the memory was so huge, it was just not practical. First of all, it wasn't practical, and second, it wasn't needed to generate all the GDS files and stuff like that, right? Generating the physical view of that was kind of pointless because we were never going to put that in a layout. That was always meant to be external memory. So
Right.
maybe we can do a similar thing here. If we can hook up a module of SRAMs, large SRAM module to the AIB bus and place it outside. And we'll call that a memory chiplet.
Yeah, that can also work. Yeah. It allows us to tomorrow, if we have to turn it into a 3D demo, it also very easily fits in with that.
Right. Yeah.
And you're foregoing the HBM interface altogether now, right?
The quirk about that is the memory controller.
The quirk about that is the memory controller. Yeah.
Right. How do we get a memory controller for that?
Mm-hmm.
I don't. I have no access. I don't have access to that kind of. Output.
Mm-hmm.
So you kind of you took notes what we are looking for, right? What kind of help we need.
Yeah.
Right. Basically, hook up, finish a little bit on the CPU core side, and then at the CPU chiplet level, put in AIB bus and hook up everything to the AIB bus. Actually, probably we should call it. Right. John has a good point that this is a right where the industry is going. Right. Maybe if we if we at the beginning say, oh, we hooked it up to AIB bus, people are gonna stop reading what we've done. Maybe we should call it OCP demo die-to-die interface, right? Or something like that. Something neutral.
Yeah.
And maybe then once we have a logical view that sets up a few chiplets, right? Multiple CPU chiplets and multiple SRAM modules. It would be cool if we can figure out a way if we can simulate all of that and show some performance differences or do studies. I don't know, Singman or maybe the guys at UCD or UCLA, if they're looking at performance trade-offs for CPU chiplets, right? In terms of memory accesses, cache misses, all that stuff, right? Maybe that's a topic to bring up with academia. If somebody is looking into how trade-offs are being made, and if they would be interested to have participate in this, and there will be popular analysis.
Okay.
Yeah, Petrus, let me know if you have a on the OSPI related discussion with the professors if you need my help with that.
Okay. Yeah. I'll speak with them in the coming weeks. Yeah, next week likely. Yeah.
Okay.
Worst case week after. Yeah.
Yeah. Okay.
Yeah.
I actually know Puneet. I have worked with him before on a separate project.
Okay.
So,
yeah, if I get an inclination from him, we can probably invite him to this call, or just have a separate call, short call with him.
Yeah. Actually,
Okay.
that's a good idea to gauge their interest in this project overall, and if they would like to also send other students to participate, and that's somebody who will benefit from this.
Yeah. All right. Yeah.
Yeah, okay. What else is on your minds? Let me take a look to the meeting minutes, see what did we talk about last time. I'm having a heck of a brain whiplash from switching between OCP tests, OCP SIPI, and OCP demo design. So I think after all my work with OCP, I'm gonna end up with CT. You know, the options. Okay, never mind. That's it. Oh shit! I forgot that this tool has a AI transcription service. So all of that is going to end up in the meeting minutes. David is getting CTE from doing too much OCP work. I need to go and edit that. Okay. Anything else on your minds on this nice Friday? How is the weather where you are, guys? I know Petrus is probably having fabulous weather.
Yeah. No complaints.
Yeah. Yeah, it's pretty nice too. I'm in my short sleeve shirt, so yeah. All right.
Okay.
If there is nothing else, last chance to say something. Going once, twice. All right. Okay, guys. Thank you very much for your time. Happy Friday. And we'll reconvene again next week.
Right.
David, I have something actually for Boone. Boone, you sent me a bunch of information on rules, but I'm probably going to need a bit of help from you to understand what the rule is actually doing. Can we schedule a time for either later this evening or next week to review the stuff that you have sent me?
But that is coming from the EDA tools and manual. Sure. It can be early next week, sir.
Yeah. So early next week. What about Monday, Tuesday, Monday, 9 o'clock?
Monday should be fine.
But Monday, 9 o'clock CST time.
Sure.
Okay. All right. Thank you.
All right.
Okay.
Thanks, everyone. Have a good one.
Thank you, everyone.
Ready?
Yep.
Yeah.
Good.
Bye-bye.
Yep. Bye-bye.
Thank you.